Hello all. In today's topic, we are going to understand about voltage regulation in a synchronous generator. First of all, what do you mean by voltage regulation? Let us assume that whenever a synchronous generator or an alternator is subjected to varying loads, that is, the voltage at the armature terminal varies to a certain extent, and how much it is varied, amount of this variation is determines the regulation of the machine. That is, let us imagine when an alternator is loaded. Generally, load is with respect to current, and whenever the alternator is loaded, the terminal voltage decreases. As the various drops in the machine starts increasing, because when as soon as you apply the load, the various losses will increase. This will bring your terminal voltage decrease, and hence it will always be the voltage will always be different than the induced EMF. So we can define voltage regulation of an alternator as the change in the terminal voltage from no load to the full load, and it is expressed as the percentage of rated voltage when the load at a given power factor is removed without change in the speed or excitation. We can represent in the form of equation percentage regulation is equal to EPH minus VPH at secondary, we are measuring at secondary VPH into 100, where EPH is nothing but induced EMF per phase and VPH is rated terminal voltage per phase. Now this voltage regulation plays a vital role in determining overall performance of your alternator. Hence there are different methods of finding out voltage regulation, out of which we have, let us note the different methods of finding are, first one is direct loading method, direct loading, second one EMF method, EMF or synchronous impedance method, and third one MMF or ampere turn method. Also we have ASA method, American Standard Ampere method, and last one zero power factor method or Portier triangle method. Generally, all the above mentioned methods other than this direct loading are valid to note only for non-salient pole machines only, because the alternators are manufactured in large capacity. So direct loading of an alternator is generally not employed for determination of the voltage regulation. So all the other methods which were employing for predetermination of voltage regulation. So today let us understand the first method, EMF method of finding out voltage regulation. This method is also called as synchronous impedance method. Generally in the EMF method, the magnetic circuit is assumed to be unsaturated. You must note that here the magnetic circuit is assumed to be unsaturated in nature. So in this method what we do, the MMFs are, that is flux, which is produced by your rotor and the stator, are replaced by their equivalent EMFs, and hence this method is also called as EMF method. So in order to determine the voltage regulation, what we require? We require armature resistance per phase of an alternator. Second one, we require open circuit characteristics, and the third one what we require is short circuit characteristics. So let me plot open circuit and short circuit characteristics. Open circuit characteristics is plotted with respect to IF versus VPH, wherein the expected open circuit characteristics graph is like this, and here this is called as air gap line. Similarly, the short circuit characteristics is plotted IF versus IL. Here this is your short circuit characteristics, that is IL is nothing but load current, short circuit current. In order to find out this, we need the short circuit ratio. So what is the short circuit ratio? It is defined as the ratio of field current which is required to produce the rated voltage on the open circuit to field current required to circulate the full load current with the armature's short circuit. In short, we can write short circuit ratio is equal to IF1 by IF2. Similarly, open circuit test. In the open circuit test, generally alternator along with different components are connected as per the circuit. Then the alternator is made to run at a synchronous speed. So you need to run the alternator at a synchronous speed with load terminals, that is secondary terminals, kept open. And here the field resistance maximum and field current will be minimum. Now varying the field current in steps and the terminal voltage at each step is noted down. So after noting down what we will plot, we will plot the graph of EPH that versus IF. So generally the shape what we had shown earlier, it takes the normal magnetization curve. So the extension of the linear portion of the OCC is nothing but it's called as air gap line of the characteristics. Similarly in the short circuit test what we do, all the connections will remain same, but here the secondary armature terminals are short circuited. Now by keeping your rheostat in the maximum position, again the rotor is made to run at the synchronous speed. Now slowly the speed is increased in steps till the rated current. Here what we will do, IL, ISC, that is short circuit current versus IF. So rated current versus the field current. Once we do, we are going to plot the OCC and SCC curve. Once OCC and SCC is plotted, we are going to determine synchronous impedance ZS. Now let me show both OCC and SCC plotted on the same curve. Now this was our OCC curve, OCC. So this is our point A versus IF. So this was your VPH. Similarly, IL to IF. So this is your short circuit curve. So this point is called as ISC. So this is B and C. So how to do this? We have to draw OCC and SCC characteristics on the same graph sheet, which will determine the field current that gives the ISC. At the same IF, we need to find the value of VPH. Now, how to find out the synchronous impedance ZS here means, here ZS is equal to open circuit voltage divided by short circuit armature current, which is the open circuit voltage here. So AB. So ZSC is equal to open circuit voltage is AB by AC. AC is your short circuit current. Since on the short circuit the terminal voltage is 0 and the whole of induced EMF is utilized to create the short circuit current. So what we get? We get EPH is equal to IA into ZS, or ZS is equal to EPH by ISC, wherein because IA is equivalent to ISC. Now once we get this, we need to measure the armature resistance of the any particular winding of a three-phase alternator. In order to measure the armature resistance, we require resistance. We need to connect an ammeter to the winding. This is what we are going to measure. So this is your rheostat, variable rheostat. So across this we are going to connect an voltage. So by applying the different ammeter and voltage ratings, we are going to obtain RA value. RA is 1.9 times V by I. So once we get the value of RA, then we are going to find out the value of XS. So XS is equal to square root of ZS square minus RA square. ZS square we have found out from the graph, RA square we have got the value now. So substituting this in EP, that is VPH cos phi plus ia ra square plus vph sin phi plus r minus ia x square. So plus for lag, minus for lead. So once we get this, we can find out the voltage regulation percentage regulation EPH minus VPH divided by VPH into 100. So this is how the voltage regulation is calculated using EMF technique. Thank you.